I want you to imagine something with me tonight. Picture yourself standing outside on a clear night, looking up at the stars. Thousands of pinpoints of light scattered across the darkness like diamonds on velvet. Each one of those lights is a sun, perhaps with its own planets, its own cosmic story unfolding across distances so vast that the light reaching your eyes tonight left those stars before you were born, before your grandparents were born, perhaps before humanity itself walked the earth. It's a humbling feeling, isn't it? That sense of being small beneath the enormousness of space. But tonight, I want to invite you to consider something even more extraordinary, something that might stretch your imagination in ways that feel almost impossible. What if everything you're looking at, this entire universe with its hundreds of billions of galaxies, each containing hundreds of billions of stars, what if all of that is just one universe among many? What if reality itself is far stranger, far more vast than even that cosmic view suggests? This isn't science fiction, though it might sound like it. This is a genuine question that physicists, cosmologists, and philosophers have been wrestling with for decades. Are we alone in reality? Not alone in the sense of, is there other life out there, but alone in a much more fundamental way. Is our universe the only universe that exists? Or are we living in what scientists call a multiverse? A reality where countless other universes exist alongside our own, perhaps forever beyond our reach, perhaps even containing other versions of ourselves living different lives, making different choices. Tonight, we're going to explore these questions together. And I want you to know right from the start that this journey is going to take us into some genuinely strange territory. We're going to talk about quantum mechanics, where particles can be in multiple places at once. We're going to discuss cosmic inflation, where the fabric of space itself expanded faster than the speed of light. We're going to wade into string theory, with its extra dimensions curled up smaller than atoms. And we're going to confront some profound questions about what it means to exist at all. But here's what I want you to remember as we go on this journey. You don't need to understand every detail. You don't need to grasp every equation or follow every logical step. What matters is the sense of wonder, the feeling of possibility, and perhaps most importantly, the permission to simply let these ideas wash over you like waves. Some will stick, some will drift away, and that's perfectly fine. There's no test at the end. There's only the mystery itself, and the strange comfort of knowing that reality might be even more extraordinary than we ever imagined. So, settle in. Get comfortable. Let your mind relax into that space between waking and sleeping, where the impossible starts to feel almost plausible. And let's begin by asking the most fundamental question of all. What exactly do we mean when we talk about the universe in the first place? What we mean when we say universe? Before we can understand whether there might be multiple universes, we need to get clear on what we mean by the word universe itself. It's a word we use so casually as if its meaning were obvious. But the more you think about it, the more complex it becomes. When most people say the universe, they're referring to everything that exists. All of space, all of time, all of matter and energy, every galaxy and star and planet, every atom and particle, all the physical laws that govern how things behave. It's the totality of existence as we know it. And for most of human history, this was a satisfying definition. The universe was everything by definition, so there couldn't be anything outside of it. The question of other universes would have seemed like nonsense, a logical contradiction. But here's where things get interesting. When physicists and cosmologists use the word universe today, they're often being more specific and more limited than that grand philosophical definition. They're usually talking about what we call the observable universe, which is something quite different. The observable universe is the region of space from which light has had time to reach us since the beginning of the universe roughly 14 billion years ago. Because light travels at a finite speed, about 186,000 miles per second, and because the universe has a finite age, there's a limit to how far we can see. Beyond a certain distance, light from those regions simply hasn't had enough time to reach us yet. That boundary, that cosmic horizon, sits at about 46 billion light-years away from us in all directions. Yes, 46 billion, not 14 billion, because space itself has been expanding all this time, stretching the distances even as light travels through them. Now take a breath and let that sink in for a moment. 46 billion light-years. It's a distance so enormous that it breaks our ability to truly comprehend it. If you could somehow travel at the speed of light, it would take you 46 billion years to reach the edge of what we can observe. And here's the thing, that's just how far we can see. It's not necessarily the edge of everything that exists. Think of it this way. Imagine you're standing in the middle of a vast fog-covered plain. The fog is so thick that you can only see clearly for about a mile in every direction. That visible region, that circle of clarity around you, is what you might call your observable plane. But does the plane end at the edge of what you can see? Of course not. It almost certainly extends far beyond your limited vision. There might be mountains out there in the fog, or oceans or cities, or other people standing in their own circles of visibility, unable to see you just as you're unable to see them. The observable universe is like that circle of visibility. It's not that there's nothing beyond it. It's that we can't see beyond it, at least not with light. And if the universe extends beyond what we can observe, if there's more space out there past our cosmic horizon, then in a very real sense, those distant regions could be considered separate universes from our own, even though they're all part of the same continuous space, all governed by the same physical laws. This is what cosmologists sometimes call a level 1 multiverse, and we'll come back to it later. But I want you to notice something important here. We've already started to blur the lines of what universe means. Is a region of space that exists, but that we can never observe or interact with part of our universe or not? It's a question that doesn't have an obvious answer, and it hints at how tricky these concepts become once you really start to think about them. But there's another way to think about the word universe that's even more interesting. Instead of defining a universe by what we can observe from a particular location, we might define it by its physical properties. We might say that a universe is a region of space-time with a particular set of physical laws and constants. In our universe, for example, the speed of light has a specific value. The strength of gravity, the mass of an electron, the way electromagnetism works. All of these properties have particular values that could, in principle, have been different. And this opens up a fascinating possibility. What if there are other regions of reality, perhaps impossibly far away, perhaps separated from us in ways we can't even visualize, where these fundamental properties are different? Where light travels at a different speed, where gravity is stronger or weaker, where matter behaves in completely alien ways? Would those regions count as different universes? Many physicists think they would, because even though they might be made of the same fundamental stuff as our cosmos, they would be so different in their behavior that calling them part of the same universe would be misleading. This is getting at something profound. The word universe is starting to fracture into multiple meanings, and which meaning you use determines whether you think multiple universes are even possible. If universe means literally everything that exists, then by definition there can only be one. But if universe means a region of space-time with particular properties and laws, then suddenly the possibility of multiple universes becomes not just conceivable, but perhaps even likely, depending on how reality is actually structured. Let me give you another way to think about this that might help. Consider the concept of world in everyday language. We sometimes talk about the medieval world, or the underwater world, or the world of professional chess. In each case, we're referring to a domain of experience, a realm with its own rules and inhabitants, even though all of these worlds exist on the same planet, in the same physical reality. The medieval world isn't a different planet. It's a different context, a different set of conditions and relationships. In a similar way, when physicists talk about multiple universes, they're often talking about different domains of reality, different contexts with different conditions, even if there's some deeper underlying reality that connects them all. Just as the medieval world and the modern world are both part of Earth's history, multiple universes might all be part of some larger framework that we don't yet understand. Over the course of human history, our understanding of the scale and nature of the universe has expanded dramatically. Ancient peoples thought the Earth was the entire universe, or nearly so, with the heavens being some kind of dome or sphere surrounding our world. Then we realized Earth was a planet among planets, orbiting the Sun. Then we discovered that the Sun was one star among billions in a galaxy. Then we found that our galaxy was one galaxy among billions, perhaps hundreds of billions, in the observable universe. Each expansion of our cosmic view required us to reimagine our place in existence, to accept that what we thought was everything was actually just a small part of something much larger. The multiverse is the latest and perhaps most dramatic expansion of this cosmic perspective. It's the suggestion that even the observable universe, with all its incomprehensible vastness, might be just one bubble, one domain, one context, among countless others. And just as people once found it difficult to accept that Earth wasn't the center of everything, many people today find it hard to accept that our entire universe might not be the center of everything either. But before you decide whether you believe in multiple universes or not, we need to understand where this idea comes from. It's not just wild speculation. It emerges from some of our best and most successful scientific theories, theories that have been tested and confirmed in thousands of experiments. The multiverse isn't something physicists made up because it sounded cool. It's something they found themselves being forced to consider, often reluctantly, when they followed the mathematical and logical implications of theories that work remarkably well at explaining what we can observe. So let's begin our journey into the multiverse by starting with perhaps the strangest place of all, the quantum realm, where reality itself seems to split and branch in ways that challenge everything we think we know about how the world works. The quantum door to many worlds. Take another deep breath with me. Let yourself relax a little more. We're about to enter the strangest territory in all of science, the world of quantum mechanics, where common sense doesn't just fail, it fails spectacularly in ways that seem almost designed to make our heads hurt. But here's what I want you to know. If quantum mechanics seems weird to you, if it feels impossible to truly understand, you're in good company. Richard Feynman, one of the greatest physicists of the 20th century, famously said, "I think I can safely say that nobody understands quantum mechanics," and he was one of its pioneers. So don't worry if this feels slippery, if it keeps escaping your full comprehension. That's the nature of quantum mechanics. It describes reality at its smallest scales, at the level of atoms and subatomic particles, and at that scale, reality simply doesn't behave the way our everyday experience suggests it should. Here's the basic strangeness we need to grapple with. At the quantum level, particles don't have definite properties until they're measured. An electron doesn't have a specific location or a specific momentum until you check. Before measurement, it exists in what physicists call a superposition, a state where it has all possible values at once, each with different probabilities. The act of measuring, of observing, somehow forces the particle to choose one specific value, collapsing all those possibilities down to a single reality. This is deeply weird. It suggests that reality at its most fundamental level is fuzzy, indeterminate, probabilistic rather than definite. And for nearly a century, physicists have been arguing about what it means. The standard interpretation, developed in Copenhagen in the 1920s by Niels Bohr and others, essentially said, look, the math works, the predictions are accurate, just shut up and calculate. Don't ask what's really happening. The wave function, the mathematical object describing all those possibilities, doesn't represent physical reality. It's just a tool for calculating probabilities. But not everyone was satisfied with this. In 1957, a young graduate student at Princeton named Hugh Everett III proposed something radical, something that seemed almost too strange to take seriously, but that has, over the decades, become increasingly influential. Everett asked a simple question. What if the wave function is real? What if all those possibilities in superposition actually exist, not just as mathematical abstractions, but as genuine physical realities? His answer became known as the many worlds interpretation of quantum mechanics, and it's one of the most profound ideas in all of science. According to Everett, when a quantum measurement happens, when a particle is forced to choose between different possible states, the universe doesn't choose. Instead, the universe splits. Every possible outcome actually happens, but in separate, non-communicating branches of reality. When you measure an electron and find it in one location, there's another branch of reality where another version of you measured it in a different location. Both outcomes occur. Both are equally real. They just happen in different worlds. Let me try to make this more concrete, even though the very concreteness feels slippery. Imagine you're about to flip a coin. In classical physics, the coin will land either heads or tails. Before you flip it, the outcome is unknown, but determined by the exact forces and angles involved. In quantum mechanics, if we could somehow make this a truly quantum coin, something governed by quantum randomness rather than classical determinism, the situation would be different. According to the standard interpretation, before you observe the result, the coin is in a superposition of both heads and tails. The wave function describes both possibilities. When you look, the wave function collapses, and you see one outcome or the other, with each having a 50% probability. But according to Everett's many worlds interpretation, when you look at the coin, the universe splits. In one branch you see heads, in another branch you see tails. Both versions of you are equally real, equally conscious, equally convinced that they've observed a definite outcome. But these two versions can never communicate with each other, can never even know about each other, because they exist in separate branches of reality that have decohered, meaning they've become so different that they can no longer interfere with each other quantum mechanically. Now, I know what you might be thinking. This sounds insane. This sounds like science fiction, like something from a comic book or a TV show about alternate dimensions. And Everett's colleagues in the 1950s largely agreed. His thesis advisor, John Wheeler, one of the most respected physicists of his generation, was initially supportive, but then became concerned that the idea was too radical, too speculative. Niels Bohr, the dominant figure in quantum mechanics at the time, dismissed it. Everett, frustrated and disillusioned, left academic physics entirely and spent the rest of his career working on defense contracts and computer science. He died in 1982, still largely unknown outside a small circle of Quantum Foundation's researchers. But something interesting happened in the decades after Everett's death. His interpretation started to be taken more seriously. Physicists began to realize that the many worlds interpretation, while strange, actually solved several profound problems in quantum mechanics. It eliminated the need for a mysterious collapse mechanism. It treated measurement as just another physical process, governed by the same quantum rules as everything else. It was, in a sense, the most straightforward reading of the quantum formalism, the one that took the mathematics at face value without adding extra assumptions about what happens during measurement. The most famous illustration of quantum strangeness is the thought experiment known as Schrödinger's cat, proposed by Erwin Schrödinger in 1935 as a way of showing how absurd the quantum world would be if it applied to everyday objects. Here's the setup. Imagine a cat in a sealed box with a vial of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers the release of the poison, killing the cat. If the atom doesn't decay, the cat lives. According to quantum mechanics, before we open the box and observe the situation, the atom is in a superposition of both decayed and not decayed. And this means, bizarrely, that the cat is in a superposition of both dead and alive. Schrödinger intended this as a reductio ad absurdum, a way of showing that quantum mechanics led to ridiculous conclusions. But Everett's interpretation takes it seriously. In the many worlds view, when the atom state becomes entangled with the cat state, the universe splits. In one branch, the atom decays, the poison is released, and the cat dies. In another branch, the atom doesn't decay, and the cat lives. There's no moment when the cat transitions from superposition to a definite state. Both outcomes are real, in separate branches of reality. When we open the box, we don't cause the cat to become dead or alive. We become entangled with the system ourselves. Our consciousness splits. In one branch, we see a dead cat. In another, we see a living cat. Both versions of us are real. Both think they've observed a definite outcome, and neither knows about the other. Now let's pause here and let this sink in for a moment. Breathe with me. I know this is a lot. If you're feeling your mind starting to slip away from full focus, that's okay. That's actually perfect for where we are right now, in this liminal space between understanding and mystery. The many worlds interpretation is asking us to accept something that feels almost unacceptable, that every quantum event is constantly creating new branches of reality, and that we're living in just one of an incomprehensibly vast number of parallel worlds. How many parallel worlds are we talking about? The mathematics suggests a number so large it's effectively meaningless. Every quantum interaction, every particle that could be in multiple states, every atom that could decay or not decay, every photon that could be absorbed or reflected, all of these are constantly creating new branches. The physicist Sean Carroll, one of the contemporary advocates of the many worlds interpretation, estimates that the number of branches that have been created since the beginning of the universe is something like 2 to the power of 10 to the power of 112. That's a 2 followed by more than 10 duodecillion zeros. It's a number so vast that writing it out would require more atoms than exist in the observable universe. In this interpretation, there are versions of you reading these words right now in countless branches of reality. In some of those branches, your life is almost identical to this one. Maybe you're wearing different clothes, or you decided to listen to this video tomorrow instead of today. But in other branches, your life diverged long ago. Maybe you chose a different career, married a different person, moved to a different city. Maybe in some branches you were never born at all, because some quantum event in your parents' past went differently. Every possible history that's compatible with quantum mechanics is actually playing out somewhere in the vast tree of branching realities. This raises profound questions about identity and consciousness. Are all those other versions of you really you? They share your past up to some point of divergence, but then their experiences become different. Are they still the same person? Philosophers and physicists have debated this intensely. Some argue that personal identity is maintained through some kind of continuity of consciousness or memory, and that these other versions, having different memories and experiences, aren't really you anymore. Others argue that they're all you, just different instances of the same underlying pattern or information. And here's something even stranger to consider. If the many worlds interpretation is correct, you never die. Or rather, you always die, but there are always branches where you continue to live. Every potentially fatal moment, every car accident you almost had, every illness you might have contracted, every random quantum event that could have gone differently, creates branches where you survived and branches where you didn't. From your subjective experience, you only ever find yourself in the branches where you survived because dead versions of you don't have experiences. This leads to what some call quantum immortality, the idea that from your own perspective, you will never experience death because there will always be branches where unlikely events conspired to keep you alive. Now, I need to be clear about something important. The many worlds interpretation is not proven. It's not something all physicists accept. In fact, it remains controversial, one of several competing interpretations of quantum mechanics, none of which can currently be distinguished by experiment. The mathematics of quantum mechanics is incredibly successful. The predictions match observations with stunning precision. But what the mathematics means, what's actually happening in physical reality, remains genuinely uncertain. Some physicists prefer the Copenhagen interpretation, which avoids talking about what's really happening and focuses just on what we can measure. Others favor pilot wave theory, proposed by Louis de Broglie and David Bohm, which says particles always have definite positions but are guided by a quantum wave that we can't observe. Still, others advocate for various collapse theories, which try to explain how and when the wave function collapses into definite outcomes. The many worlds interpretation has gained ground in recent decades, partly because of its mathematical elegance. It requires no additional assumptions beyond the basic quantum formalism. It doesn't need a collapse mechanism or a division between quantum and classical realms. Everything is quantum, and everything evolves according to the Schrödinger equation, which describes how wave functions change over time. The apparent collapse is just an illusion created by decoherence, the process by which quantum systems become entangled with their environments and effectively separate into non-interfering branches. But whether the many worlds interpretation is correct or not, it demonstrates something important for our exploration of the multiverse. It shows that the idea of parallel realities, of multiple versions of history all being equally real, isn't just science fiction. It emerges naturally, almost inevitably, from one straightforward reading of our most successful theory of microscopic reality. The quantum multiverse, if it exists, isn't optional. It's not something nature chooses to create or not create. It's built into the fundamental structure of how quantum systems evolve. And this quantum multiverse would be radically different from the kind of multiverse we might imagine in science fiction. These aren't separate bubble universes floating in some higher dimensional space. These are branches of reality that all occupy the same space, the same 3 dimensions, but which have become separated in an abstract mathematical space called Hilbert space. You can't travel between them. You can't send signals from one branch to another. They're separate in a way that's much more fundamental than mere distance. Yet they're all real, all equally existing, all containing conscious observers who think they're experiencing the one true timeline of events. Every decision you make, every coin flip, every quantum measurement is splitting reality into multiple branches, and all of them continue to exist and evolve. You right now are just one thread in an incomprehensibly vast fabric of branching histories. Let that settle in your mind as we prepare to move on. The quantum multiverse is one possibility, one framework for understanding how reality might be structured. But it's not the only type of multiverse that physics suggests might exist. There's another kind of multiverse arising from a completely different area of physics that we need to explore. This one doesn't come from quantum mechanics, but from cosmology, from our attempts to understand the origin and evolution of the universe itself. And in some ways, it's even stranger than the quantum multiverse, because it suggests that space itself might be infinite, that there might be regions of reality so far away that light from them will never reach us. Regions that could be considered separate universes, not because they've split from ours, but because they were always separate, always beyond our reach. Let's rest here for a moment before we continue. Take a slow breath. Notice how you're feeling. Are you still with me, or has your mind started to drift into that pleasant space between thoughts? Either way is fine. We're in no hurry. We have all the time we need to explore these mysteries. And when you're ready, we'll continue our journey into the next type of multiverse, one born from the violent expansion of space itself in the first fraction of a second after the Big Bang. The inflationary multiverse, bubble universes. Close your eyes again and try to imagine nothing. Not darkness, because darkness is something. Not empty space, because space itself is something. Just nothing at all. No matter, no energy, no time, no dimensions. Pure non-existence. It's impossible to truly imagine, isn't it? Our minds rebel against the concept. Even when we try to think of nothing, we're thinking of something. Usually a void, an emptiness. which is itself a kind of container. Now imagine that this nothing suddenly becomes something, not through any process because processes require time and time doesn't exist yet, just a spontaneous emergence of existence from non-existence. And then imagine that this tiny seed of existence, far smaller than an atom, begins to expand. But not in the gentle, steady way you might picture a balloon inflating. Instead, it expands violently, exponentially, doubling in size every fraction of a fraction of a fraction of a second. In less than a trillionth of a second, this tiny quantum fluctuation expands to larger than a galaxy, then larger than a supercluster of galaxies, then larger than the observable universe. This is cosmic inflation, and it's one of the most successful theories in modern cosmology. Proposed by Alan Guth in 1980 with crucial modifications by Andre Linde and others in the early 1980s, inflation explains several otherwise puzzling features of our universe. It explains why the universe is so flat, so uniform, why it has the same temperature in all directions even though those directions seem like they should never have been in contact with each other. It explains where the tiny irregularities in density came from that eventually grew into galaxies and clusters. And it does all this with a surprisingly simple mechanism. The mechanism is something called a scalar field, often called the inflaton field, that permeates space. Think of it like a field of energy, somewhat analogous to the electromagnetic field, but different in its properties. In the very early universe, in the first fraction of a second after whatever process created space and time, this inflaton field was in a high-energy state, what physicists call a false vacuum. And here's the remarkable thing about this state. It created a kind of repulsive gravity. We normally think of gravity as attractive. Mass pulls on mass. But Einstein's general theory of relativity allows for something strange. Under certain conditions, matter or energy with negative pressure can create a gravitational repulsion instead of attraction. The high-energy state of the inflaton field had exactly this property. It pushed space apart instead of pulling it together. And because this energy was a property of the vacuum itself, of space itself, as space expanded, more space was created with the same energy density, creating more repulsive gravity, causing more expansion, in a runaway process that doubled the size of space roughly every 10 to the minus 35 seconds. This expansion was staggeringly fast, much, much faster than the speed of light. Now, before you object that nothing can travel faster than light, let me clarify. Individual objects can't travel through space faster than light, but space itself can expand at any rate. There's no speed limit on the expansion of the fabric of space-time itself. During inflation, regions of space that started out near each other, perhaps close enough that light could have connected them, were pushed so far apart so quickly that they became causally disconnected. Light from one region could never reach the other, no matter how long it traveled, because the space between them was expanding faster than light could cross it. Eventually, the inflaton field decayed out of its high-energy state and into a lower-energy state. This process is called reheating, and it converted the energy of the inflaton field into a hot, dense soup of particles and radiation. This is what we call the Big Bang, or at least the hot, dense phase of the early universe that we usually associate with that term. The Big Bang wasn't the beginning of everything. It was the end of inflation, the moment when the exponential expansion stopped and the universe transitioned into a slower, more gentle expansion driven by the matter and radiation that inflation had created. Now, inflation solves a lot of problems in cosmology, and there's good observational support for it. The pattern of temperature variations in the cosmic microwave background, the afterglow of the Big Bang that we can still detect today, matches the predictions of inflation with remarkable precision. Most cosmologists accept that something like inflation probably happened. But here's where things get interesting for our discussion of the multiverse. It turns out that in most models of inflation, once it starts, it never completely stops. Let me explain what I mean by that. Imagine space as a vast ocean of the high-energy inflaton field, all of it expanding exponentially. Now imagine that in some regions the field decays and inflation ends, creating a bubble universe, a pocket of space where the inflaton has transitioned to its low-energy state and created a hot Big Bang. Our entire observable universe would be inside one such bubble. But outside that bubble, in the vast majority of space, inflation is still going on. The inflaton field is still in its high-energy state, still driving exponential expansion. And here's the crucial point. Inflation is happening so fast that even though bubbles are constantly forming, even though regions are constantly transitioning out of inflation, the inflating volume grows faster than the bubbles can eat into it. For every region that stops inflating, dozens or hundreds or thousands of regions continue to inflate and expand. The total volume of inflating space increases without limit. Inflation becomes eternal into the future. This is called eternal inflation, and it has a staggering implication. If eternal inflation is correct, then our universe, meaning our bubble, our region that underwent reheating and produced a hot Big Bang, is just one bubble among countless others. There are other bubbles forming constantly, each creating their own hot Big Bangs, their own universes. And these universes, these bubble universes, or pocket universes as they're sometimes called, can be forever separated from each other. The inflating region between them is expanding so fast that light from one bubble can never reach another. They are causally disconnected, separate universes in a very real sense, even though they all emerged from the same underlying inflating space. Alan Guth has famously called this the ultimate free lunch. The idea is that the total energy of a universe might actually be zero. The positive energy of all the matter and radiation is exactly balanced by the negative gravitational potential energy. Creating a universe doesn't require borrowing energy from anywhere or violating conservation laws. It's energetically free. And if it's free to create one universe, there's no reason the process can't create an infinite number of them. Now let's think about what these other bubble universes might be like. Are they similar to ours? Do they have the same laws of physics, the same fundamental constants? This brings us to what cosmologists call the Level 2 multiverse, in contrast to the Level 1 multiverse we mentioned earlier. The Level 1 multiverse, you'll recall, is the idea that space might be infinite, extending far beyond our observable horizon. In this scenario, if you traveled far enough, impossibly far beyond what we can see, you'd eventually encounter regions where the arrangement of matter is different from here, but where the laws of physics are the same. In an infinite space, every possible arrangement of matter that's consistent with those laws would occur somewhere, infinitely many times in fact. There would be other regions with galaxies and stars and planets. And if space is truly infinite, there would even be perfect copies of Earth, of our solar system, of you living lives identical to yours up to this moment. This Level 1 multiverse doesn't require any new physics. It's just a consequence of infinite space, plus the cosmological principle, the idea that the universe is roughly the same everywhere on large scales. But the Level 2 multiverse, the eternal inflation multiverse, is different. Here, different bubble universes might have different physical properties. The laws of physics themselves might vary from bubble to bubble. How is this possible? It has to do with something called spontaneous symmetry breaking. In the very early universe, at extremely high temperatures, the fundamental forces that we observe today might have been unified into a single force. As the universe cooled, this symmetry broke, and the forces separated into the electromagnetic force, the weak nuclear force, and the strong nuclear force. The exact way this symmetry breaks can happen in different ways, leading to different outcomes, different effective laws of physics. Think of it like water freezing into ice. Water is symmetric. It looks the same in all directions. But when it freezes, ice crystals form with particular orientations. The symmetry is broken. Each crystal has a specific structure, even though the underlying physics is the same. In a similar way, each bubble universe might undergo symmetry breaking differently, leading to different particle masses, different force strengths, different numbers of dimensions that remain large instead of curling up small. In some bubble universes, electrons might be heavier or lighter. In others, gravity might be stronger or weaker. Some bubbles might have stable atoms and chemistry, and the possibility of complex structures like stars and planets and life. Others might be stillborn, collapsing back on themselves immediately, or expanding so fast that matter can never clump together. The vast majority of bubble universes might be completely inhospitable to any form of complexity, let alone life. And this brings us to one of the most controversial aspects of multiverse theories, the anthropic principle. If there are countless bubble universes with different properties, and if the vast majority of them can't support life, then it's not surprising that we find ourselves in one of the rare bubbles where the conditions are right for life to exist. We couldn't observe a lifeless universe because observers require life. This is called the weak anthropic principle, and it's essentially a selection effect. We're biased observers, only able to exist in certain types of universes, so we shouldn't be surprised that we find ourselves in one of those types. Some physicists find the anthropic principle unsatisfying. They want a theory that predicts the specific values of the fundamental constants from first principles, not one that says, well, the constants could be anything, and we just happen to live where they're right for us. It feels like giving up on explanation, but other physicists argue that the anthropic principle is perfectly legitimate. If the multiverse is real, if our universe really is just one of many with varying properties, then appealing to anthropic reasoning is no different from explaining why we live on Earth rather than Jupiter by pointing out that Earth has the right conditions for life while Jupiter doesn't. Let me paint you a picture of what this eternal inflation multiverse might be like. Imagine an infinite ocean of exponentially expanding space. Within this ocean, bubbles are constantly forming, each one a universe like ours. Each bubble expands, but not as fast as the surrounding inflating space. So the bubbles never collide, never merge. They remain forever isolated from each other, each one growing and cooling and evolving according to its own physics. Inside each bubble, a Big Bang occurs. Matter and radiation fill the space. Over billions of years, gravity pulls matter together into clumps, stars form, galaxies coalesce, planets condense from disks of gas and dust. In some bubbles, this process leads to complexity, to chemistry, perhaps to life and consciousness. In others, the conditions are wrong and the universe remains simple and empty. And all the while, in the vast inflating bulk surrounding all these bubbles, new bubbles are forming. The process never ends. There is no final state, no ultimate configuration. Eternal inflation is truly eternal, producing bubble after bubble after bubble, each one a universe with its own history, its own fate, its own potential for meaning and complexity. You are living inside one such bubble. Everything you've ever known, every person who's ever lived, every star and galaxy in the observable universe, all of it exists within a single bubble that formed about 14 billion years ago. Beyond our bubble, beyond the exponentially expanding space that separates us from other bubbles, there might be infinitely many other universes, each as vast and ancient as our own, each filled with wonders we can never observe. How does this make you feel? Does it make you feel small, insignificant, lost in an infinite foam of bubble universes? Or does it fill you with wonder, with the extraordinary realization that existence is far grander than we ever imagined? There's no wrong answer. Both responses are natural. Both are human. We can feel both at once, actually, that simultaneous sense of insignificance and significance, of being tiny parts of something incomprehensibly vast, yet still being here, still existing, still mattering within our own context. Let yourself rest with these ideas for a moment. Breathe. We're not done yet, but we've covered a lot of ground, moved through some genuinely challenging concepts. It's okay if your mind is getting tired, if you're starting to drift. That's part of the journey we're on tonight. This movement between understanding and letting go, between grasping ideas and releasing them. When you're ready, we're going to explore another type of multiverse, one that emerges from perhaps the most ambitious theory in all of physics, a theory that attempts to unify quantum mechanics and gravity to explain all the forces and particles of nature as vibrations of tiny strings. This is string theory, and it brings with it a multiverse of its own, one even more vast and strange than eternal inflation. The string theory landscape. Let me ask you to imagine something with me. Picture the smallest thing you can think of. Maybe an atom, about a 10/1000th of a meter across. Or go smaller to the nucleus of an atom, about 100,000 times smaller than that. Or even smaller to a proton or electron, the fundamental particles that make up atoms. Now imagine going smaller still, much, much smaller, about 1 billion times smaller than a proton. At this scale, far below anything we can observe with even our most powerful instruments, string theory suggests that reality is made not of point-like particles, but of tiny, vibrating loops of energy, like infinitesimally small rubber bands, oscillating in complex patterns. This is string theory, and it's one of the most mathematically beautiful and conceptually ambitious ideas in all of physics. The core insight is simple, almost elegant. Instead of treating particles like electrons and quarks as fundamental point-like objects with no internal structure, string theory says they're actually different vibration modes of the same underlying object, a string. Just as a violin string can vibrate in different patterns to produce different musical notes, these fundamental strings can vibrate in different patterns, and each pattern corresponds to a different particle. One pattern gives you an electron, another gives you a quark, another gives you a photon. All of physics, in this view, is the music of vibrating strings. But string theory comes with something strange. For the mathematics to work, For the theory to be mathematically consistent and to properly describe gravity and quantum mechanics together, space can't have just the 3 dimensions we experience plus time. String theory requires extra dimensions, typically 6 or 7 additional spatial dimensions beyond the 3 we're familiar with. These extra dimensions aren't big like length, width, and height. They're curled up, compactified into shapes so small that we can't perceive them, much smaller than atoms, existing at every point in space, but invisible to us because of their tiny size. Think of it like this. If you look at a garden hose from far away, it looks one-dimensional, like a line. But if you zoom in close, you see it's actually a cylinder, with a circular dimension curled around its length. At every point along the hose, there's a tiny circle perpendicular to the main axis. String theory suggests that space is like this at every point. There are 3 large dimensions we can move through, but at every point, there are also 6 or 7 additional tiny dimensions, curled up in complex geometric shapes called Calabi-Yau manifolds, which are too small for us to access or observe directly. Now here's where the multiverse comes in. There are many different ways these extra dimensions can be curled up, many different possible shapes for the Calabi-Yau manifolds. And the specific shape determines the physical properties of the universe at large scales. The masses of particles, the strengths of forces, what we think of as the laws of physics. All of this depends on the geometry of the compactified dimensions. Different shapes give you different physics. How many different shapes are possible? This is where things get truly staggering. Early estimates suggested there might be something like 10 to the power of 500 different ways to compactify the extra dimensions in string theory. That's a 1 followed by 500 zeros. More recent estimates are even higher. This vast array of possible universes is called the string theory landscape, and each point in this landscape represents a different possible universe with different physical laws. To put that number in perspective, the total number of atoms in the observable universe is estimated to be around 10 to the power of 80. The number of possible string theory vacua, the technical term for these different configurations, is vastly larger than that. It's larger than any number that has physical relevance in our universe. It's a number so large that even trying to comprehend it is futile. Now, you might ask, if there are so many possible configurations, which one describes our universe? And this is where the landscape becomes controversial. In the early days of string theory, physicists hoped that there would be one unique configuration, one special point in the landscape that the theory would naturally select, and that this configuration would explain why the fundamental constants have the values they do. They wanted string theory to predict the mass of the electron, the strength of gravity, all the parameters of the standard model of particle physics, deriving them from first principles. But that hope hasn't been realized. Instead, what string theorists found was this enormous landscape of possibilities. And this has led to 2 very different reactions. Some physicists, like Leonard Susskind at Stanford, embrace the landscape. They combine it with eternal inflation to create what's called the string landscape multiverse. In this picture, different bubble universes from eternal inflation have different string theory vacua, different ways their extra dimensions are compactified. Our universe is just one bubble with one particular configuration, but there are countless other bubbles with different configurations, different physics. In this view, the reason our universe has the particular constants it does isn't because they're somehow special or required by theory. It's anthropic. Most configurations don't allow for complex structures, stars, chemistry, life. We find ourselves in one of the rare configurations that does, not because it's preferred by the theory, but because we couldn't exist anywhere else. The vast landscape of string theory, combined with eternal inflation, naturally explains apparent fine-tuning without needing to invoke design or special initial conditions. Other physicists find this deeply unsatisfying. Paul Steinhardt at Princeton has been particularly critical. He argues that if string theory predicts 10 to the 500th different universes, then it predicts nothing. It loses all predictive power. Any observation we make can be accommodated by finding some region of the landscape where it's expected. This isn't science, critics say. It's not testable or falsifiable. It's giving up on explanation. The debate intensified in 2018 when several papers argued that stable universes with positive vacuum energy, like ours appears to have, might not be allowed in string theory at all. The landscape might actually be a swampland, a region of theory space that looks mathematically consistent but doesn't actually correspond to stable physical realities. If this is true, it could be good news for string theory's predictive power, because it would dramatically reduce the number of possible universes. But it would also present a problem. Our universe appears to have positive vacuum energy, dark energy pushing space apart. So if that's not allowed in string theory, maybe string theory is wrong. As of now, this debate remains unresolved. String theorists are actively working on these questions, trying to determine what the theory really predicts, and whether the landscape is as vast as it appears, or whether there are as yet undiscovered principles that select out a much smaller set of possible universes. It's frontier science, genuinely uncertain, with smart people on different sides of the debate. But let's step back from the technical controversies for a moment and think about what the string theory landscape, if it's real, would mean for our place in reality. Imagine that there really are 10 to the 500th different possible universes, each with different particle masses, different force strengths, different numbers of dimensions. The vast majority of these universes would be simple, featureless. In some, gravity might be so strong that any matter immediately collapses into black holes. In others, it might be so weak that matter never clumps together at all. In some, there might be no electromagnetic force, making atoms impossible. In others, the strong nuclear force might be too weak to hold atomic nuclei together. Only an infinitesimally small fraction of these universes would have the delicate balance of properties needed for complexity, for stars that live billions of years, for chemistry that allows complex molecules, for planets where life could potentially evolve. And we, of course, find ourselves in one of those rare universes. Not because we're special, but because we're observers, and observers can only exist in certain types of universes. This is where the multiverse starts to intersect with deep questions about purpose and meaning. If our universe is just one random configuration among countless others, does that make it less meaningful? Does it strip away the sense that there's something special or intentional about the way things are? Or does it actually enhance the wonder, the realization that out of incomprehensible vastness and variety, complexity and consciousness emerged here, in this bubble, in this configuration, against extraordinary odds? There's something called the principle of mediocrity in cosmology, the idea that we should expect to be typical rather than special. If there's a multiverse, we should expect our universe to be a fairly typical one among those that can support observers. And interestingly, some physicists have used this principle to make predictions. If our universe is typical of observer-containing universes, what should we expect to see? What properties should it have? And remarkably, some of these anthropic predictions have matched observations. The value of dark energy, for example, the mysterious force causing the universe's expansion to accelerate, falls within the range that anthropic reasoning suggests, even though there's no other known explanation for why it has the value it does. Let yourself sit with this for a moment. The string theory landscape, if it's real, is a multiverse of a very different sort than the quantum many worlds or even the eternal inflation bubbles. It's not about branching timelines or separated regions of space. It's about different ways that the fundamental structure of reality can be configured. Different points in an abstract mathematical landscape, each corresponding to a different possible universe with different laws. And if eternal inflation is also correct, then different bubbles in the inflating space might explore different points in this landscape, making the string theory landscape physically real rather than just mathematically possible. We're deep in the territory of speculation now, of ideas that push the boundaries of what can be tested and verified, and I want to acknowledge that directly. String theory remains unproven. We don't have experimental evidence that strings exist. We don't know if the extra dimensions are real. We can't test whether different bubble universes have different string theory vacua. These are theoretical possibilities, extrapolations from mathematical frameworks that we hope describe reality but might not. And yet, there's something compelling about the internal logic of it all. String theory emerged from attempts to unify quantum mechanics and gravity. The mathematics is extraordinarily rich and beautiful, connecting areas of pure mathematics that seemed unrelated. The theory has made surprising predictions that later turned out to be true in other contexts. It might be wrong about describing our universe, but it's not arbitrary or baseless. It's a serious attempt to understand reality at its deepest level, and the multiverse implications, however strange, follow naturally from the theory's structure. As we prepare to move forward, I want you to take a deep breath with me. We've explored 3 different types of multiverse now. The quantum many worlds, where reality branches with every measurement, the eternal inflation bubbles separated by exponentially expanding space, and the string theory landscape of different possible configurations of physical law. Each is strange in its own way. Each challenges our intuitions, and each emerges from serious attempts to understand different aspects of physics. But we're not done yet. There are other multiverse proposals, other ways that physicists and philosophers have imagined reality might be structured. And there's a deeper question we haven't fully addressed. If multiple universes exist, could there be other versions of you? How would that work? What would it mean? Let's continue exploring these mysteries, moving now into some of the more exotic and speculative multiverse ideas, and then circling back to think about the personal implications of living in a potentially infinite reality. Mathematical universes and other proposals. There's a physicist at MIT named Max Tegmark who has proposed something so bold, so philosophically radical, that it makes the other multiverse theories we've discussed seem almost modest by comparison. Tegmark suggests that mathematical structures don't just describe the universe, they are the universe. Every mathematically consistent structure exists in exactly the same sense that our physical universe exists. Not as abstract possibilities, not as potential realities, but as actual, concrete, existing universes. This is called the mathematical universe hypothesis, or the level 4 multiverse in Tegmark's classification system. To understand it, we need to take a step back and think about the relationship between mathematics and physics. In physics, we use mathematics to describe reality. We write equations that capture the behavior of particles, fields, space-time. The Schrödinger equation describes quantum mechanics. Einstein's field equations describe gravity. These mathematical structures correspond to physical reality with extraordinary precision. The predictions we can calculate from the equations match observations with remarkable accuracy. But here's the question Tegmark asks: why does this work so well? Why is reality so perfectly describable in mathematical terms? One possibility is that reality is fundamentally mathematical, that the physical universe is itself a mathematical structure, and we're just discovering its properties. This is a form of Platonism, the idea that mathematical objects have a kind of existence independent of human minds, existing in some abstract realm of forms or ideas. Tegmark takes this further. He argues that if mathematical structures have this kind of existence, then all mathematical structures should exist, not just the one that happens to describe our observable universe. Every consistent mathematical framework corresponds to an actual universe somewhere in the level 4 multiverse. There would be universes governed by different mathematical laws, different symmetries, different numbers of dimensions, different fundamental structures. Some might be simple, like cellular automata following basic rules. Others might be incomprehensibly complex, and our universe, with its particular mathematical structure, would be just one among this vast ensemble. This is deeply strange. It suggests that there's no fundamental difference between physical existence and mathematical existence. To be a mathematically consistent structure is to exist, and if that's true, then the level 4 multiverse is the ultimate multiverse, encompassing not just different configurations of our physics, not just different quantum branches or inflation bubbles, but literally every possible universe that can be consistently described mathematically. Most physicists find this too speculative, too metaphysical. There's no way to test it, no observational consequence that would confirm or deny it. And there are conceptual problems too. How do we define which mathematical structures count as universes? Do all of them have observers? If not, how do we explain why we find ourselves in this particular structure rather than another? The anthropic principle becomes almost infinitely complicated in a level 4 multiverse. But Tegmark's proposal does something interesting. It provides a kind of ultimate explanation for why our universe has the laws it does. Because all possible mathematical laws are instantiated somewhere, and we find ourselves in this one because we're structured in a way that requires these particular laws. It's the final generalization of anthropic reasoning, applied not just to the constants within our physics, but to the structure of physics itself. Let me describe another exotic multiverse proposal, one coming from a completely different direction. This is Roger Penrose's conformal cyclic cosmology, and it's based on a radically different view of time and the universe's fate. In the standard cosmological model, the universe began in the Big Bang and will continue expanding forever, eventually reaching a state of maximum entropy, where all stars have burned out, all black holes have evaporated, and nothing interesting can happen anymore. This is called the heat death of the universe, the cold, dark, eternal end state. Penrose suggests something different. He proposes that the remote future of our universe, This state of maximum entropy, with nothing but scattered radiation, might actually be equivalent to the Big Bang of a new universe. The idea relies on something called conformal geometry, a way of looking at space-time that cares about angles but not distances. In the far future, when matter has all decayed and only massless particles like photons remain, distance becomes meaningless in a certain mathematical sense, and Penrose shows that you can smoothly transition from this far future state to a new Big Bang, creating what he calls an aeon, a cosmic cycle. Our universe, in this view, is one aeon in an eternal sequence. Before our Big Bang, there was a previous aeon that ran through its own history and reached its own far future. After our aeon ends, there will be another Big Bang beginning another aeon. And this process continues forever in both directions, past and future, an endless series of cosmic cycles, each lasting trillions upon trillions of years before transitioning to the next. This is a multiverse in time rather than space. Different aeons are separate universes, but they're connected through these conformal transitions. And remarkably, Penrose claims there might be observational evidence for this. He and his collaborators have reported finding unusual patterns in the cosmic microwave background, concentric circles that they interpret as the signatures of colliding black holes from the previous aeon, imprinted on the structure of the Big Bang that started our aeon. Most cosmologists are skeptical of these claims, arguing that the patterns are probably just statistical flukes. But if Penrose is right, we might actually have observational evidence of a universe that existed before ours, a truly extraordinary possibility. There are other multiverse proposals too, though I won't go into all of them in detail. Some theories suggest that new universes might form inside black holes, creating a kind of evolutionary multiverse where universes that produce many black holes have more offspring universes. Some versions of quantum cosmology suggest that new universes might spontaneously tunnel into existence from quantum vacuum fluctuations, a process that might be happening constantly. Some theorists have even suggested that our universe might be a simulation running on a computer in some higher-level reality, making us part of a multiverse of simulated worlds. What I want you to notice is the sheer variety of multiverse proposals. They come from different areas of physics, different interpretations of quantum mechanics, different approaches to cosmology, different philosophical frameworks. Some of them might be compatible with each other. For example, eternal inflation and the string landscape fit together naturally. Quantum many-worlds operates at a different level entirely and could coexist with cosmological multiverses. But some proposals are mutually exclusive, representing fundamentally different visions of how reality is structured. And this brings us to a crucial point. We don't know which, if any, of these multiverse theories is correct. They're not established science. They're possibilities, implications of theories that are themselves not fully confirmed. The multiverse is still in the realm of speculation, informed speculation based on serious physics, but speculation nonetheless. It might turn out that none of these ideas is right, that the universe is singular and unique, that our observable region is all there is. But even if the multiverse is speculative, even if we can never definitively prove it exists, the fact that these ideas emerge naturally from our best attempts to understand physics is significant. It tells us something about the structure of our theories, about the kinds of explanations that seem to work, about the mathematical patterns that connect different areas of physics. And it opens up questions that are worth thinking about, even if we can't answer them definitively. Let yourself rest here for a moment. We've covered a lot of ground, explored a dizzying array of possible realities. If you're feeling overwhelmed, that's natural. These ideas push the limits of what we can conceptually grasp. They're meant to. They're describing possibilities that are so far beyond everyday experience that our minds strain to accommodate them. But now I want to bring things back to something more personal, more immediate. If the multiverse is real, if there really are countless other universes out there or countless quantum branches of this universe, what does that mean for you? Could there be other versions of you living different lives? And if so, what would that mean for identity, for choice, for the significance of your experiences? Let's explore these questions next, bringing the cosmic back down to the human scale where it intersects with our actual lives. Could there be other versions of you? Take a moment and think about a decision you made recently. Maybe something small, like whether to have coffee or tea this morning, or something larger, like a career choice or a relationship decision. Now imagine that you had made the opposite choice. How would your life be different? Would you be happier, sadder, more successful, more fulfilled? Would you still be essentially the same person? Or would that different choice have sent your life down a completely different path? We all wonder about these things. We imagine alternate versions of our lives, roads not taken, possibilities that didn't unfold. It's a fundamental part of being human, this ability to imagine counterfactuals, to think about what might have been. But the multiverse theories we've been discussing suggest something remarkable. Those counterfactual versions of your life might not just be imaginary. They might be real, actually existing in other branches of reality or other regions of the multiverse. Let's start with the most straightforward case, the Level 1 multiverse of infinite space. If space extends infinitely beyond our observable horizon, and if matter is distributed more or less randomly throughout that infinite space, then somewhere out there, incomprehensibly far away, there should be regions where matter arranged itself in exactly the same configuration as it did here. There should be another Earth, with another solar system, another galaxy that looks just like the Milky Way. And on that other Earth, there should be someone exactly like you, with the same body, the same memories, the same personality, living a life identical to yours right down to this exact moment, reading these exact words. This isn't mysticism or speculation. It's a straightforward mathematical consequence of infinite space plus finite possible configurations. There are only so many ways that atoms can be arranged within a given volume. The number is enormous, something like 10 to the power of 10 to the power of 122 for a region the size of the observable universe. But it's still finite. And if space is infinite, then every possible configuration must occur not just once, but infinitely many times. So there would be infinitely many copies of you out there in the vast infinite space beyond what we can see. Most of them would be living lives very similar to yours because the initial conditions that shaped your life would be similar. But some would be different. Maybe in one copy you chose coffee instead of tea. In another, you took a different job. In another, you never met your partner or your best friend. Every possibility that's compatible with the laws of physics is realized somewhere in the infinite expanse. Now, it's crucial to understand that these other versions of you are impossibly far away. The nearest one, statistically speaking, would be at a distance of about 10 to the 10 to the 122 Hubble volumes away. That's not a distance we can express in light years or any conventional unit. It's so incomprehensibly far that light from that region will never reach us, no matter how long we wait. These other versions of you are beyond any possibility of contact or communication. They exist if this model is correct, but they're completely separate from your experience. The quantum many worlds version of other yous is quite different. In the many worlds interpretation, every time a quantum measurement occurs, the universe splits. And because your body and brain are made of atoms, because your neurons fire based on chemical reactions governed ultimately by quantum mechanics, your choices and experiences are constantly creating quantum branches. Every moment, countless versions of you are splitting off, experiencing slightly different outcomes, making slightly different choices. These quantum versions of you aren't separated by vast distances in space. They're separated by something more abstract, by the branching structure of the quantum wave function. They occupy the same space you do, in a sense, but in different branches of reality that have decohered and can no longer interact. When you make a decision, it's not that you're choosing one outcome over another in any absolute sense. Rather, different branches of you are experiencing different outcomes, and each one thinks they made a specific choice. This raises fascinating and troubling questions about identity and free will. If every possible outcome of every quantum event is realized in some branch, then in what sense are you making choices? There are branches where you chose one thing and branches where you chose another. The subjective experience of choosing feels singular, feels like you're determining a unique outcome. But if many worlds is correct, you're actually just one thread in an incomprehensibly vast fabric of branching histories, and every option is taken by some version of you. Some philosophers argue that this actually enhances rather than diminishes free will. Yes, all outcomes occur, but you, the specific version of you in this branch, are still determining which branch you're in. Your choices still matter for your subjective experience, for the particular history you're living through. The fact that other versions of you made different choices doesn't make your choices less real or less significant. Each branch has its own reality, its own validity. But other philosophers find this unsatisfying. If all choices are made by some version of you, then choice seems to lose meaning. And there's a disturbing corollary called quantum immortality that I mentioned earlier. In the many worlds view, you can never experience death because there will always be branches where unlikely events conspired to keep you alive. From your subjective perspective, you will always find yourself in branches where you survived because the dead versions of you don't have experiences to notice their death. So you, the experiencing consciousness, will always find yourself alive, perhaps becoming older and older, surviving against increasingly improbable odds in some eternally persisting branch of reality. Most physicists think quantum immortality is probably wrong, that it relies on a mistaken understanding of how probability and observation work in the many worlds interpretation. But even if it's wrong, it illustrates how weird the implications get when you take the theory seriously and try to apply it to subjective experience. The eternal inflation multiverse offers yet another possibility for other versions of you. If there are countless bubble universes with different initial conditions but the same physical laws, then somewhere among those bubbles there should be some with histories similar to our own. Some of them might have galaxies that formed in similar patterns, stars and planets that evolved similarly. And on some of those planets, life might have evolved, and some of that life might have produced beings remarkably like humans, perhaps even beings with your specific genetic configuration or something close to it. These wouldn't be exact copies of you in the way that the level 1 infinite space versions would be. The histories would have diverged much earlier at the level of galaxy formation or earlier, but they might be similar enough that we could meaningfully call them versions of you. Same basic biology, similar environment, similar challenges and experiences. Different in details but recognizable as variations on the same theme. And if the string landscape is real, if different bubbles have different physical laws, then there might be even stranger versions of you. Perhaps in some universes the laws allow for different kinds of chemistry, different kinds of biological complexity. Maybe there are conscious beings in those universes who have experiences somewhat analogous to yours, but in contexts so alien that we can barely imagine them. Are those versions of you? It depends on how we define identity, on what we think makes you you. This question of identity across multiverses is profound. What makes you you? Is it your body? The specific arrangement of atoms? If so, then the level 1 infinite space copies are genuinely you, because they have the exact same atomic arrangement. But is it your memories and experiences, your personal history? If so, then those copies aren't really you anymore once their experiences diverge from yours, even if they started out identical. Is it some kind of continuity of consciousness? A thread of subjective experience? If so, then the quantum branches might all be you until they decohere, after which they become separate entities with separate streams of consciousness. Philosophers have been arguing about personal identity for millennia, long before anyone thought about multiverses. The classic thought experiments involve things like teleportation. If you're disassembled atom by atom and reassembled elsewhere, is the reassembled person still you? Or what about gradual replacement? If your neurons were slowly replaced one by one with functionally identical artificial neurons, would you still be you after the process was complete? The multiverse adds new dimensions to these old questions. If there are quantum branches of you, are they all you? If there are spatial copies of you in distant regions, are they you or just people very much like you? If there are versions of you in other bubble universes with slightly different physical laws, are they still you in any meaningful sense? These questions don't have obvious answers. They depend on what theory of identity you accept, and there's no consensus. But here's what I find most interesting about all this. Whether or not other versions of you exist in some objective sense, the possibility changes how we think about our own lives. If every choice is realized somewhere, if every possible version of your life is playing out in some branch or bubble or distant region, does that make your particular life more meaningful or less? You could see it as diminishing. If there are infinite copies of you, if every decision leads to branches where you chose differently, then maybe your specific choices don't matter as much. You're just one thread in an incomprehensibly vast fabric, one voice in an infinite chorus. Your joys and sorrows, your triumphs and failures are all replicated infinitely many times. You're not unique, you're not special. But you could also see it as enhancing meaning. Yes, there might be other versions of you, but this version, the one experiencing this moment right now, is still unique. Your subjective experience, your particular stream of consciousness, is yours alone. The other versions, even if they exist, don't diminish your reality. They exist in their own contexts, living their own lives. And within your branch, within your bubble, within your region of reality, Your choices matter. They shape your experience, determine which version of you you're going to be. Think of it like this: even in a single universe, without any multiverse, you're not unique in many ways. There are billions of other humans on Earth right now, each having their own experiences, feeling their own emotions, living their own stories. Does the existence of all those other people make your life less meaningful? Number. Your particular life, your particular perspective, is still uniquely yours. The multiverse just extends this to a cosmic scale. There might be countless beings throughout reality, countless versions of you even, but this moment, this experience, this consciousness reading these words right now, that's still singular, still precious, still mattering in its own context. Let yourself sit with that thought for a moment. Breathe. Whether you're alone in reality or one of infinite copies, this moment is still real. Your experience is still valid. And perhaps there's something comforting in that, something liberating. If the multiverse is real, then you don't have to be perfect. Somewhere, other versions of you are making different choices, living different lives. But here, now, in this branch or this bubble or this region, you're living this life. And that's enough. That's everything, actually. As we move forward, I want to shift our attention to a more practical question, one that often comes up when people first encounter multiverse theories. If these other universes exist, can we ever detect them? Can we find evidence? Or is the multiverse forever beyond our ability to test and verify? This is where science and philosophy intersect most directly, where we have to grapple with what makes an idea scientific and what it means to understand reality. The evidence question. Can we ever know? Let's talk about something that makes many physicists uncomfortable. Actually, let's talk about something that has sparked genuine anger and frustration within the physics community. The question is simple, but the answer is complicated. Is the multiverse a scientific theory? Science is supposed to be based on observation and experiment. We develop theories to explain what we observe. We make predictions based on those theories. We test the predictions. If the predictions match observations, the theory is supported. If they don't, the theory is rejected or modified. This is the basic method that has made science so successful, that has given us our understanding of everything from atoms to galaxies, from DNA to quantum fields. But the multiverse presents a problem. If other universes are by definition beyond our ability to observe, separated from us by infinite space or exponentially inflating regions or quantum decoherence, how can we test whether they exist? How can we make predictions about them? How can we gather evidence for or against them? And if we can't do any of these things, then isn't the multiverse just metaphysics, philosophy, rather than physics? This is the criticism that has been leveled most forcefully by physicists like George Ellis and philosophers of science who worry that physics is losing its way. The philosopher Karl Popper famously argued that for a theory to be scientific, it must be falsifiable. There must be some possible observation that would prove it wrong. If no observation could ever disprove a theory, if it's compatible with any outcome, then it's not making testable claims about reality. It's just storytelling, however mathematically sophisticated. And at first glance, the multiverse seems to fail this criterion. If we can never observe other universes, how could we ever falsify the claim that they exist? You can't prove a negative. You can't demonstrate that something doesn't exist if you have no way to detect it. So the multiverse seems to be unfalsifiable, which would make it unscientific by Popper's criterion. But the physicists who take the multiverse seriously push back against this. They argue that the multiverse isn't just a wild speculation, it's a consequence of theories that are themselves testable and well confirmed. Quantum mechanics has been tested countless times. The predictions match observations with extraordinary precision. The many worlds interpretation is one straightforward reading of quantum mechanics, arguably the most straightforward one, requiring no additional assumptions. If you accept quantum mechanics, and if you follow its mathematics consistently, many worlds seems to follow naturally. So if quantum mechanics is a scientific theory, and many worlds is a consequence of quantum mechanics, then many worlds is scientific too, even if we can't directly observe the other branches. Similarly, cosmic inflation has observational support. The pattern of temperature variations in the cosmic microwave background matches inflation's predictions, and eternal inflation, the idea that inflation never completely stops, is a generic feature of most inflation models. You don't have to add it by hand, it emerges naturally from the physics. So if inflation is a scientific theory and eternal inflation is a consequence of inflation, then the bubble universe multiverse is scientific too, even if we can't observe other bubbles. String theory is more controversial because it hasn't made any testable predictions yet. But it's not arbitrary either. It's a mathematically consistent framework that unifies gravity and quantum mechanics, something that other theories have failed to do. The landscape of possible universes emerges from the theory's structure, not from speculation. So even though we can't test string theory directly yet, it's not unscientific in the way that, say, astrology is unscientific. The defenders of the multiverse also point out that there might be indirect ways to test these ideas, even if we can't observe other universes directly. Let me explain what I mean by this. In the case of the quantum many worlds interpretation, we might be able to distinguish it from other interpretations by looking for extremely subtle quantum effects. Some physicists have suggested that if we could isolate a large enough system from its environment and maintain quantum coherence, we might be able to observe something called quantum revival, where branches that have separated start to interfere with each other again. This is incredibly difficult, probably impossible with current technology, but it's not ruled out in principle. If we could observe such an effect, it would support many worlds over collapse interpretations. For the eternal inflation multiverse, there's a slightly better possibility. If our bubble universe collided with another bubble in the past, it might have left a mark on the cosmic microwave background, an unusual pattern of hot and cold spots that we could potentially detect. Several groups of cosmologists have searched for such collision signatures. So far, they haven't found any convincing evidence, but the search continues. It's at least conceivable that we might someday detect a signal that could only be explained by a collision with another bubble universe. There's also the anthropic approach to testing the multiverse. If the multiverse predicts that we should find ourselves in a typical universe among those that can support observers, then we can test this by seeing whether our universe's properties match what we'd expect from this principle. And surprisingly, some anthropic predictions have worked. The value of the cosmological constant, the dark energy that's causing the universe's expansion to accelerate, falls within the narrow range that anthropic reasoning suggests, even though there's no other known explanation for why it has the value it does. Now, I want to be honest about something. These indirect tests are nowhere near as definitive as we'd like. The collision signatures might not exist, or they might be too subtle to detect. The anthropic predictions are often criticized as being too flexible, capable of accommodating almost any observation, and quantum revival experiments are probably beyond our technological capabilities for the foreseeable future. But there's something else to consider. The history of science is full of ideas that seemed untestable when they were first proposed, but later became testable as technology and methods improved. Atoms were considered almost metaphysical entities in the 19th century, unobservable in principle. But by the early 20th century, we had ways to study them. The interior of the Sun was thought to be forever beyond our reach. But now we can use neutrino detectors to observe the nuclear reactions in the Sun's core. The expansion of the universe was considered impossible to observe in the 1920s, but Hubble observed it shortly thereafter. So maybe the multiverse is like this. Maybe it seems untestable now, but in 50 or 100 years, we'll have methods we can't currently imagine. Maybe quantum technologies will advance to the point where we can probe the many worlds interpretation more directly. Maybe cosmological observations will become precise enough to detect subtle anomalies that point to other bubble universes. Maybe we'll discover new physics that constrains the string landscape and makes specific predictions about our universe's properties. Or maybe not. Maybe the multiverse really is beyond our ability to test forever. And if that's the case, then we have to grapple with a difficult question. Should we believe in ideas that can't be tested? Some physicists and philosophers say no. Without testability, we're not doing science. We're doing speculative metaphysics, which is fine as philosophy, but shouldn't be confused with empirical science. These critics worry that if we give up on testability, we're giving up on what makes science special, what separates it from other ways of thinking about the world. Others say the criterion is too strict. They point out that many of our best theories involve entities or aspects that aren't directly observable. We believe in quarks, even though we can never observe a free quark in isolation. We believe in the interior of black holes, even though no information can escape from beyond the event horizon. We believe in the Big Bang, even though we can't observe it directly, only its aftermath. Science often requires inferring the existence of unobservable things based on their effects on observable things. And if multiverse theories are genuine consequences of well-tested theories, if they're not add-ons but natural implications of frameworks that work well at explaining what we can observe, then maybe we should provisionally accept them, even if we can't test them directly. Not with the same confidence we have in things we can test repeatedly, but not dismissing them entirely either. There's also a pragmatic argument. Even if we can't test the multiverse directly, thinking about it might lead us to new insights, new ways of formulating questions, new connections between different areas of physics. The history of physics is full of ideas that were valuable even before they were testable, because they clarified thinking or suggested new avenues of research. Let me tell you about a controversy that illustrates all of these tensions. In 2020, several news outlets reported that NASA had detected a parallel universe in Antarctica where time runs backwards. The story went viral on social media. People were fascinated and excited. A parallel universe, proof that they exist. But the story was nonsense. What actually happened was that the Antarctic Impulsive Transient Antenna, a balloon-borne experiment designed to detect cosmic rays, had observed some anomalous signals that were hard to explain with conventional particle physics. One speculative paper suggested that these signals might be explained by hypothetical particles related to a cosmological model involving a kind of mirror universe. But this was just one possible explanation among many, highly speculative, and not something the ANITA team itself had proposed. The physicists involved were frustrated and angry. Peter Gorham, the leader of the ANITA experiment, issued a statement clarifying that they had not detected a parallel universe, that the news reports had wildly misrepresented the science, and that the most likely explanation for the anomalous signals was probably something much more mundane, like contamination or instrumental artifacts or known but rare processes in particle physics. This episode illustrates the problem with how multiverse ideas filter into popular consciousness. There's a hunger for the exotic, for the confirmation that reality is stranger than we thought. And that hunger can lead to sensationalism, to taking speculative ideas and presenting them as established facts. The multiverse becomes a kind of cultural Rorschach test, where people project their hopes and fears about the nature of reality. But here's what I want you to take away from all of this. The multiverse remains uncertain. We don't know if it's real, we might never know for sure. But the fact that the idea emerges from serious attempts to understand the universe is significant. It tells us something about the structure of our theories, about the kinds of explanations that physicists find compelling, about the mathematical patterns that connect quantum mechanics and cosmology and string theory. Whether the multiverse exists or not, thinking about it forces us to grapple with deep questions about the nature of explanation, about what makes a theory scientific, about what we can know and how we can know it. And these questions are valuable in themselves, regardless of the final answer about the multiverse. So where does this leave us? Uncertain, but thoughtfully uncertain. The multiverse might be real. It might not be. We might someday find evidence for it. We might not. And that's okay. That's actually the normal state of frontier science. This tension between what we know and what we're trying to understand, between certainty and speculation, between observation and theory. Take a deep breath with me. We're nearing the end of our journey now, and I want to shift gears one more time. We've talked about the physics, about the different types of multiverses and how they might be tested, but there are deeper questions too, questions about meaning and purpose, about what it means to exist in a potentially infinite reality. Let's explore those questions now, bringing our cosmic journey back to human concerns, to the philosophical and even spiritual implications of the multiverse. The philosophical implications. There's something both terrifying and liberating about the idea that we might live in a multiverse. Terrifying because it can make us feel small, insignificant, lost in an infinity of realities where everything that could happen does happen. But liberating too because it releases us from the burden of uniqueness, from the need to be the only version of things, the final answer. Let me start with one of the most profound implications. What the multiverse does to our understanding of causation and explanation. Throughout history, humans have looked at the world and asked, why? Why does the sun rise? Why does water freeze? Why do living things reproduce? And science has been incredibly successful at answering these questions with chains of cause and effect, with mechanisms and processes that connect one event to another. But some questions seem different. Why does the universe exist at all, rather than nothing? Why do the fundamental constants have the values they do? Why is the speed of light exactly 299,792,458 meters per second rather than some other value? These questions feel different because they're not asking about relationships within the universe, but about the universe itself, about the framework within which everything else happens. Before the multiverse, there were basically two kinds of answers to these questions. One was religious or metaphysical. The universe is the way it is because some higher power or deeper reality made it that way, chose these values, set up these conditions. The other was that these questions are meaningless, that asking why the universe has its properties is like asking what's north of the North Pole, a category mistake that assumes the question makes sense when it doesn't. The multiverse offers a third option. Maybe the fundamental constants don't have special values that need explaining. Maybe they vary across different universes, and we find ourselves in one where they allow for complexity and life because we couldn't exist anywhere else. This is the anthropic principle again, but now we can see it in a broader context. It's not giving up on explanation, it's changing the type of explanation from why this specific value to why do we observe this value? And the answer to the second question might be much more straightforward. Because we're observers, and observers can only exist where the conditions permit observation. Think about an analogy. Why is Earth located in the habitable zone around the Sun, where temperatures allow liquid water? Before we knew about other planets, this might have seemed like a profound mystery requiring special explanation. But now we know there are billions of planets in our galaxy alone. Some are too hot, some too cold. Most are completely inhospitable. Earth's location isn't special. It's a selection effect. Life developed here because the conditions were right, and we naturally find ourselves somewhere conditions are right, because we couldn't have developed anywhere else. The multiverse extends this logic cosmically. The universe's properties aren't special. There are countless universes with different properties. We find ourselves in one where physics allows complexity, because we're complex beings. Simple as that. But this raises a troubling question about the nature of probability and confirmation. If literally everything that can happen does happen somewhere in the multiverse, then no observation can surprise us, because whatever we observe has to be happening in some universe, and we're necessarily in one where we can make observations. This seems to rob science of its predictive power. How do we test theories if any outcome is compatible with it happens somewhere in the multiverse? This is called the measure problem in cosmology, and it's one of the deepest conceptual challenges facing multiverse theories. The problem is that in an infinite multiverse, especially in eternal inflation, every possible outcome occurs infinitely many times. So you can't just count how many times each outcome occurs and calculate probabilities that way. Infinity divided by infinity isn't well defined. You need some principled way to compare infinite sets, to define what typical means in an infinite context. Physicists and cosmologists have proposed various solutions to the measure problem, different ways of defining probabilities in an infinite multiverse. But there's no consensus. It's an active area of research, genuinely difficult, touching on foundational questions in mathematics and philosophy as well as physics. Here's another deep question. What does the multiverse do to the concept of laws of nature? We usually think of physical laws as universal, applying everywhere and everywhen. The law of gravity, the laws of thermodynamics, the principles of quantum mechanics. These are supposed to be the same throughout the cosmos. But if different bubble universes have different physical laws, or if the quantum many worlds allows for different outcomes of the same initial conditions, then in what sense are there universal laws? One answer is that there might be meta-laws, deeper principles that govern which physical laws are possible, how they vary across the multiverse, how different universes are generated. String theory, for example, is sometimes viewed this way. The theory itself would be universal, but the specific physics of each universe would depend on local conditions, on how the extra dimensions are compactified, on which vacuum state the inflaton settled into. Another answer is that laws aren't fundamental at all but emergent, arising from deeper mathematical structures or information-theoretic principles. The physicist John Wheeler famously suggested it from bit, the idea that physical reality emerges from information. In this view, what we call physical laws might be patterns in how information flows and processes, and different patterns might emerge in different contexts or regions of a larger informational structure. These are deep philosophical waters, and I don't pretend to have answers. But I want you to see how the multiverse forces us to reconsider concepts we thought we understood, to question assumptions we didn't even know we were making about the nature of reality, causation, and explanation. Let's turn to something more personal now. What does the multiverse mean for free will and moral responsibility? This is especially acute in the quantum many worlds interpretation. If every choice you make is realized in some branch, if there are versions of you that chose differently, then are you really free? And if you're not free, can you be held responsible for your actions? I think this is actually a confusion, a category mistake. Free will isn't about whether alternate possibilities exist somewhere. It's about whether you, the conscious decision maker, have genuine agency in determining which possibility you actualize in your branch, in your experience. The fact that other branches exist where you chose differently doesn't make your choice less real or less yours. You're not those other versions. You're this version, and this version's choices matter for this version's life. In fact, you could argue that the many worlds interpretation actually enhances moral responsibility rather than diminishing it. If collapse theories are correct, then the outcome of your decision might be partly random, determined by quantum fluctuations you can't control. But in many worlds, every outcome occurs, and which branch you find yourself in depends on your actual decision-making process, on the physical states in your brain that constitute your choice. There's no randomness, no cosmic dice roll determining outcomes, just the deterministic branching of possibilities with you as a participant in that branching. But I'll be honest, I'm not entirely satisfied with that answer. The question of free will in a multiverse, especially in many worlds, remains genuinely puzzling to me. It feels like our intuitive concepts of choice and agency don't quite fit the structure of reality that quantum mechanics seems to describe. Maybe that's okay. Maybe we shouldn't expect our intuitions, evolved to deal with everyday objects and social interactions, to perfectly capture the nature of reality at its most fundamental level. There's also a question about meaning and purpose. If every possible history occurs somewhere in the multiverse, does anything matter? If all outcomes are equally real, does that make our particular outcomes less significant? I think this is another confusion. Meaning isn't something that exists objectively in the universe, multiverse or otherwise. Meaning is something we create, something we experience. Your life has meaning because you experience it as meaningful, because you care about your relationships, your projects, your experiences. The fact that there might be other versions of you experiencing different meanings doesn't diminish your meaning. It exists in your context, in your branch or bubble or region, and that's where it needs to exist. That's where you live. Think about it this way. Even in a single universe, even without any multiverse, your life is temporary. You'll die. The people you love will die. Eventually, the sun will expand and consume the earth. Eventually, all stars will burn out, and the universe will reach heat death. Does this make your life meaningless? Does the fact that everything is temporary make your joys less joyful, your loves less valuable? I don't think so. Meaning exists in the experiencing, in the living, not in some eternal, unchanging permanence. The multiverse just extends this. Yes, there are other versions of you, other possible lives, other branches or bubbles or regions. But this life, the one you're living right now, is still yours, still real, still meaningful in its own context. The multiverse doesn't take that away. It just situates it in a larger framework. And there's something almost beautiful about this, something that speaks to an old spiritual insight, that we should let go of attachment to outcomes, that we should embrace the moment we're in, rather than constantly wishing we were somewhere else, someone else, living some other life. If the multiverse is real, then all those other lives are being lived, but not by you, by other versions of you in other contexts. And you're here, in this moment, in this reality. And that's enough. That has to be enough, because it's what is. Let yourself feel whatever emotion arises from these thoughts. Maybe it's peace, acceptance of your place in something vast. Maybe it's anxiety, discomfort with the uncertainty and strangeness. Maybe it's wonder, awe at the sheer scope of possible existence. All of these are valid. All of these are human responses to ideas that push the boundaries of what we can comfortably imagine. We're almost done with our journey now. Just a little further to go. I want to bring everything together, to think about what it means to live with uncertainty, to be humans confronting the possibility of a reality far stranger and vaster than our ancestors ever imagined. And then finally, to let go, to settle into the peace of not needing to know everything, of being able to rest in wonder and mystery. Living with uncertainty. Take a slow breath with me. We've traveled a long way tonight, through quantum branches and inflating bubbles, through string landscapes and mathematical structures, through questions of evidence and identity and meaning. And if you're feeling a bit overwhelmed, a bit dizzy from the conceptual journey we've taken, I want you to know that's perfectly normal. What we've been discussing isn't easy. These ideas push against the limits of what human minds can comfortably grasp. But here's something I want to acknowledge directly. We don't know if any of this is true. The multiverse might be real, or it might not be. We might live in a quantum superposition of countless branches, or we might not. There might be bubble universes beyond our horizon, or there might not be. The universe might be singular and unique, or it might be one among infinitely many, and we might never know for certain. This uncertainty isn't a failure. It's not something to be embarrassed about or to hide. It's simply the current state of our understanding, the frontier where knowledge gives way to speculation, where observation meets theory, and neither quite constrains the other enough to give us final answers. And there's something honest and real about acknowledging this uncertainty, about sitting with it rather than pretending we have answers we don't have. Science isn't a collection of facts. It's a process, an ongoing conversation between observation and theory, between what we see and how we interpret it. And at the frontiers, that conversation is messy, uncertain, full of competing ideas and unresolved questions. The multiverse is at that frontier right now. It's not established science. It's not something you have to believe or accept, but it's also not meaningless speculation. It's a serious attempt to follow the implications of our best theories, to see where the mathematics and logic lead, even when they lead to strange and counterintuitive places. And here's what I find beautiful about this. We live in an age where we can even ask these questions. For most of human history, the universe seemed small and comprehensible. The earth, the sky, the heavens above. Maybe a few thousand stars. Maybe a deity or deities watching over everything. It was all contained, all explicable within frameworks that made intuitive sense. But as we've learned more, the universe has gotten stranger and larger and more mysterious. We discovered that stars are suns, that galaxies are vast collections of stars, that the observable universe contains hundreds of billions of galaxies. We learned that space and time are flexible, that matter and energy are interchangeable, that particles can be in multiple places at once. At every step, reality has turned out to be weirder than we expected, more vast, more subtle, more surprising. The multiverse is potentially the next step in this expansion of understanding. It's the suggestion that everything we can see, this entire observable universe with its hundreds of billions of galaxies, might be just a tiny part of something incomprehensibly larger. And whether this turns out to be true or not, the fact that we can formulate the question, that we can think seriously about what it would mean and how we might test it, that's extraordinary. That's a testament to human curiosity and imagination and analytical skill. Let me tell you something personal. When I first encountered multiverse ideas years ago, I had a strange reaction. I felt simultaneously insignificant and amazed. Insignificant because if the multiverse is real, I'm just one person in one universe among countless others, living one life among infinite possible lives. My problems, my achievements, my entire existence, all of it becomes vanishingly small against the backdrop of infinite reality. But I also felt amazed because I'm part of this. However small I might be, however briefly I might exist, I'm here, I'm conscious. I'm capable of understanding enough to even contemplate these possibilities. I'm made of atoms that were forged in stars, governed by quantum mechanics that allows for multiple worlds, existing in a universe that might be one among many. That's not nothing. That's actually quite something. And I've come to think that this dual response, this combination of humility and wonder, is exactly the right attitude to have toward the multiverse and toward reality more generally. Yes, we're small. Yes, we're temporary. Yes, there might be incomprehensible vastness beyond our reach, but we're also here. We're also conscious. We're also capable of asking questions about the nature of existence itself, and that's worth something. That means something. There's an ancient philosophical position called cosmicism, associated with writers like H.P. Lovecraft, that emphasizes human insignificance in the face of cosmic vastness. The universe is indifferent to us, vast beyond comprehension, and humans are just temporary blips with no cosmic importance. This can lead to a kind of nihilism, a sense that nothing matters because everything is ultimately meaningless against the backdrop of infinity. But I think cosmicism misses something important. Yes, the universe is vast and probably indifferent, but meaning isn't something the universe provides. Meaning is something we create, something that emerges from consciousness and care and connection. Your relationships matter because you care about them. Your projects matter because they matter to you. Your experiences have significance because you experience them as significant. None of this requires cosmic validation. It's local, it's personal, but it's real. The multiverse, if it exists, doesn't change this. Whether you're the only version of yourself or one of infinite versions, this version, the one having these thoughts right now, is still real. Your experiences are still genuine. Your life is still worth living. The scope of reality beyond your experience doesn't diminish the reality of your experience. And here's something else. The multiverse might actually be comforting in a strange way. It means you don't have to be perfect. You don't have to live the one perfect life, make all the right choices, never screw up, because if the multiverse is real, other versions of you are living all the other possibilities anyway. This version of you, the one in this branch or this bubble, just has to be this version. And that's enough. It also means the universe isn't as fragile as it might seem. If eternal inflation is correct, if new universes are constantly being created, then existence itself is robust, ongoing, inexhaustible. Even if our particular universe eventually reaches heat death, even if all the stars burn out and all the black holes evaporate, there will still be other bubbles, other universes, other chances for complexity and consciousness to emerge. Existence isn't a one-time thing that could have failed to happen. It's a process, potentially eternal, potentially infinite. Now, I want to be clear. I'm not saying you should believe in the multiverse. I'm not saying you should base your life philosophy on speculative physics. What I'm saying is that thinking about the multiverse, engaging with these ideas, even if they remain uncertain, can change how we see ourselves and our place in reality. It can humble us, showing us we're not the center of everything. But it can also inspire us, revealing that reality is more grand and mysterious than we ever imagined. And maybe that's the real value of cosmology, of physics, of all our attempts to understand the universe. Not just the practical applications, though those are valuable, not just the satisfaction of solving problems, though that matters too, but the expansion of perspective, the cultivation of wonder, the recognition that we're part of something vast and strange and beautiful, something that we're only beginning to understand. You don't need to remember all the details I've shared tonight. You don't need to understand eternal inflation or string theory or quantum decoherence. What I hope you'll take with you is simply this. Reality might be far stranger and more vast than it appears. We might live in a multiverse, or we might not. But either way, we're here, we're conscious, we're capable of asking these questions and contemplating these possibilities. And that's remarkable. That's worth noticing. That's worth appreciating, even as we drift towards sleep. Let yourself relax now. Let go of trying to understand everything, to hold all these concepts in your mind at once. It's okay to not know. It's okay to be uncertain. The universe has existed for 14 billion years and will likely exist for trillions more. You don't need to figure it all out tonight. You don't need to figure it all out ever, really. You just need to be here, in this moment, part of this vast, mysterious existence. Breathe with me. Feel yourself settling, relaxing, letting the questions drift away. We're almost at the end of our journey. Just a little further, and then you can rest completely. Can let yourself slip into that space between waking and sleeping where thoughts dissolve and consciousness merges with the mystery. One universe or many, this moment is yours. We've traveled far tonight, haven't we? Through quantum worlds and cosmic bubbles, through mathematical landscapes and philosophical puzzles. We've asked questions that might never be answered. Are we alone in reality? Are there other versions of you living different lives in parallel worlds? Is our universe unique, or is it one among infinitely many, a single note in an incomprehensible symphony of existence? And here at the end, I want to bring it all back to something simple, something immediate. Right now, in this moment, you exist. You're here. You're breathing. You're conscious. You're having an experience, this particular experience of being you, right now, in whatever place you are, whatever circumstances you find yourself in. This moment is real. It doesn't matter if there are quantum branches where you're doing something else. It doesn't matter if there are bubble universes with different physics. It doesn't matter if there's a level 1 multiverse with spatial copies of you infinitely far away. This moment, this consciousness, this life, this is yours. And it's enough. In fact, it's everything. Because you don't experience the other branches or bubbles or regions, even if they exist. You experience this, right here, right now, this breath, this thought, this gradual relaxation as the day draws to a close and sleep approaches. That's your reality. Not the theoretical multiverse, not the abstract possibilities, but this concrete, immediate, present experience. And whether you're alone in reality or one of infinite versions, this moment has value. The people you love, the experiences you cherish, the meanings you've created in your life. None of that is diminished by the possibility of other universes. It exists here, in your context, in your story, and that's where it needs to exist. That's where it's real. I sometimes think about the night sky, about looking up at the stars the way our ancestors did thousands of years ago. They saw the same stars, the same moon, the same planets moving through the constellations. But they had no idea what they were looking at. They thought the stars were lights on a celestial sphere, or gods, or the souls of the dead. They had stories and myths to explain what they saw. Beautiful stories, meaningful stories, but stories that were wrong about the physical nature of reality. We know more now. We know the stars are distant suns. We know the universe is vast and old and expanding. We know about quantum mechanics and relativity and cosmic inflation. We've pushed back the boundaries of ignorance, explained phenomena that our ancestors thought were inexplicable. But we've also discovered new mysteries, new questions that they couldn't even have formulated. And the more we learn, the more we realize how much we don't know. The multiverse might be the next chapter in this ongoing story of discovery. Or it might be a detour, an interesting idea that turns out to be wrong. We don't know yet. We might not know for a long time, perhaps not in our lifetimes, but that's okay. Not knowing is part of the adventure, part of what makes existence mysterious and wonderful, rather than solved and finished. I want to leave you with a thought, a comfort as you drift towards sleep, whether the multiverse is real or not, whether you're the only you or one of infinite versions, you are here, now. And that's a miracle in its way. Think about all the improbable events that had to occur for you to exist. The formation of Earth, the evolution of life, the specific sequence of events that led to your parents' meeting, to your conception, to every choice and accident and coincidence that shaped your development. The odds were astronomically against you existing. And yet here you are. If the multiverse is real, then maybe existence isn't as improbable as it seems. Maybe in an infinite reality, every possibility is realized somewhere. But you're not experiencing infinite reality. You're experiencing this reality, this one. the one where all those improbable events aligned to create you, to create this moment, to create the possibility of you lying here tonight, thinking about quantum mechanics and cosmic inflation and the nature of existence itself. That's extraordinary. Hold on to that thought as you let go of all the others. You are here. You exist. You're part of something vast and strange and beautiful, something we're only beginning to understand. And that's enough. That's more than enough. That's everything. Before I let you go, I want to ask something of you. If you've enjoyed this journey tonight, if these ideas have sparked something in you, some sense of wonder or curiosity or peace, consider subscribing to this channel. Consider sharing this with someone who might appreciate it. Consider leaving a comment with your thoughts, your reactions, your own questions about the nature of reality. We're all in this together, all conscious beings trying to understand our place in existence. And sharing these explorations, these questions, these moments of wonder, that's part of what makes us human. But for now, let yourself rest. Let the questions go. Let the theories and equations and possibilities fade away. There's nothing more you need to understand tonight. There's nothing more you need to figure out. The universe will still be here tomorrow, still mysterious, still beautiful, still full of wonders we haven't discovered yet. And you'll be here too, ready to meet another day, to live another moment of this remarkable, improbable, meaningful life, whether there's one universe or many, whether you're alone in reality or one of countless versions. This moment is yours. This breath, this consciousness, this gentle drift toward sleep. Own it, appreciate it, and then, when you're ready, let it go. Thank you for joining me on this journey through the possible multiverses. Thank you for your curiosity, your patience, your willingness to contemplate ideas that stretch the imagination. Thank you for being here, for existing, for being the particular consciousness that you are. Sleep well, dream deeply, and know that whether you wake up in this universe or somehow, impossibly, in another, you'll still be you. You'll still be here. You'll still be part of this grand, mysterious, infinitely interesting cosmos. Rest now. The multiverse can wait. The questions can wait. For now, there's just this: breathing, relaxing, letting go. Just this moment, singular and precious, in whatever reality we happen to call home. Good night.